What happens when the world's most radical architect tries to revive a 100-year-old building?
This project obviously stands and falls with structure. I mean, this is a structural masterpiece.
How is one of the world's tallest residential skyscrapers even standing?
Columns are what make a building stand up. You take away that structural support and
how do you create a building that would have been impossible just 10 years ago?
Building in water is incredibly difficult. I mean, you've got to hold back an entire river while you're building.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now their secrets are revealed, discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? Ever-growing cities are in a constant battle for space, risking demolishing the old to make way for the new. But in Antwerp, Belgium, one of Europe's busiest ports, a forgotten 100-year-old building has been transformed beyond imagination. A groundbreaking architect has turned this historic firehouse into a landing pad for an extension that is truly out of this world. Challenging engineers to float the new addition effortlessly above the original building.
It leans forwards, it's backwards, it's completely off-center on the legs.
Manufacturing the entire structure off-site and then shipping it in massive 400-ton pieces.
We're dealing with making sure we protect this precious building that lies underneath.
Breathing new life into every inch of its new home. This is the Antwerp Port House. So, how did they build it? The Antwerp Port Authority, the government body that controls the busy port, needed a new home. They decided on a long-forgotten firehouse in the center of the industrial complex. It needed some serious work if it was going to function as their new headquarters. But they didn't want to demolish the original listed building.
Adding to existing historical structures is a real challenge. You've got the technical challenge of being able to work around and load and repair what can be quite old and historic material of the building. But then you've also got the aesthetic and the kind of heritage issues as well. You need to build something that's going to be true to the original history and aesthetic of the structure, or complement it in quite a stark and interesting way.
They brought in one of the world's most famous architects, Zaha Hadid, to come up with a solution. Her visionary designs, like the Guangzhou Opera House, were known for pushing engineering to the limits. This would be her last project, completed before her untimely death in 2016. Joris Pauwels would oversee the project on the ground.
This is maybe the biggest and most prominent existing building we've taken on to develop into a new overall project. And it's definitely a challenge, but it's something that we relish. It gives all kinds of new perspectives on how to deal with existing fabric, urban fabric.
They had to figure out how to build a futuristic extension to create extra space to house new offices, while protecting a beautiful historic building that would form the rest of the Port Authority's new headquarters.
The original design had 4 equal facades, meaning there's no front entrance. 4 facades were equally important. So we definitely wanted to preserve that quality of the existing building by building a volume on top and not blocking visually one of the main facades.
The architects also wanted to preserve the building's central courtyard. Conservation specialist Philippe Lemonnier was charged with protecting this piece of Antwerp's past, making sure the radical design didn't destroy the building or rob it of its original identity.
We can see in the typology of a fire station there are a lot of elements. One you can see on the right side is that there are a lot of gates for fire trucks, and then you have the backside in the middle of the facade, the dry tower. Those elements are very important for a fire station.
Studying the plans for the firehouse gave the architects an idea, one that would honor the original design and let them build something out of this world. It turns out, the building was never actually finished.
It was built in 1921, and the original design of the fire station had a big tower on top, which is twice the size of the building, very extravagant. It was never built, and which made us consider an extension on top of the existing building as a kind of contemporary endpoint to the existing building.
This monumental extension not only brings the building into the 21st century, it completes the vision of the original architect. The plan was to build a precision-engineered, futuristic extension over 20 meters above the historic building to house new offices, supporting the 1,500-ton structure with 2 massive concrete legs, and to join the new extension to the firehouse through the old tower where the firemen used to hang their hoses to dry. The engineers got to work figuring out how to support the massive steel structure above the 100-year-old building without damaging it.
This project obviously stands and falls with structure. I mean, this is a structural masterpiece. We'd like our buildings to float if we can. So we definitely try to minimize the points and keep this idea of a large hovering volume over the existing building. The new building cantilevers out over the square in front of the existing building. It's quite a dramatic effect pointing towards the city center of Antwerp. The structure of the new building is a steel structure. It's held by 2 concrete pillars.
The engineers built the 2 concrete legs to hold up the new offices, with the front leg designed to wildly lean out. It looked dramatic, but without precise calculations, risked dropping the brand new building on top of the firehouse.
Because the front leg is leaning out at an angle, it's going to want to push out at the top and slip under the building at the bottom.
They decided to connect the front and back legs at the top and bottom, turning the structure into a massive concrete ring, with the bottom part of that ring underground.
By connecting these 2 legs at the top, they are kept from falling out of the top, and at the bottom, stopped from slipping in.
The 2 pillars are obviously not vertical, so we have a very dramatically inclined front pillar, which needs the concrete ring to keep it from falling over the square. So that's why this ring is very important as a structural element.
The ring is joined just under the massive steel and glass structure, and the bottom connects 3 stories underground in the car park, keeping the legs in place and letting them support the weight of the extension. The top section stops the giant concrete leg from falling over, and the bottom stops it sliding out from under the massive steel structure. Then the whole thing is steadied by another 4 interconnected steel supports. The engineers did all this whilst barely touching the old firehouse.
We try to keep the impact on the existing building very minimal, and that is equally important when we created this structural ring, which goes through the foundation work of the existing building. So it's a very minimal connection, both structurally, where we connect the foundations, as well as physically, where we introduced a small staircase leading up to the entrance hall inside the existing building. We've got a 2-story underground car parking, so it's 2 stories down. Underneath that, so at the 3rd basement level, if you like, that's where we made the connection between the foundation of that inclined front pillar and the central pillar which rests in the courtyard.
What did the conservation specialist think of this radical approach? Did it do justice to the original building?
The opportunity to do the second feat at the inside of the building, in the courtyard. But we still needed to have the aspect of a courtyard. You can fill it up with feats and structure, then you have no more courtyard and you have no more lights inside. You can use even more this space. So the engineer and Zaha Hadid tried to find a way that you could have this structure, but with a kind of subtlety that these are sculptural elements in the inside. And so you can see that those elements even not touch the old structure, just landing inside the building, and they make possible that this big volume above our heads is standing over there.
With the gigantic concrete legs in place, the engineers were ready to tackle the futuristic glass structure. But constructing it was going to be a bigger undertaking than anyone had imagined.
Having the new building floating in midair, it's important that that's not a super heavy construction, so it's a steel structure. It also is a sustainable structure, so we looked at a whole number of possibilities of constructing the building. We did a lot of analysis with the contractor to see how they could build platforms, how they could get enough people up there.
To preserve the original building and realize the precise design, the engineers decided to build almost all of the new extension in a factory 90 kilometers away.
It was clear after initial analysis that building the steel structure off-site in big modules, shipping them to site and installing them was a much faster and more economical way of constructing the building.
Normally with steel structures, you build upwards with scaffolding support and welding as you go. But in this case, they were building over the existing structure. You're looking at a lot of scaffolding support with all the risks of building over and around this listed precious building. So what do? You build it 90 kilometers away in 400-ton pieces and ship it in.
So building the structure of the new building off-site in factory means it's much more controlled in terms of tolerances, making sure everything is completely right. They even installed a temporary structure to ship the modules on boats to the location. And then all they had to do is lift them in place, so it's a much faster construction procedure to build the overall volume. The structure of the new building is built in 6 separate steel parts, 2 steel pieces per level, and they were lifted in place and then assembled on top of the existing building.
The 100-meter long, 60-meter high and 20-meter wide steel structure was broken up into 6 enormous 400-ton pieces and shipped from the factory 90 kilometers away on massive barges. The builders used a remote-controlled dolly system to offload these giant sections.
So it's both light construction, it's a lightweight construction time, which is important, and also the kind of environmental concern that we had. So this is achieved by having this steel structure made off-site and coming on-site by boat.
The scale of this job is immense. Just look at the size of the platforms that are used to drive off the sections from the barges. They're each the size of a truck. It just seems mad that this is the safest and quickest and most efficient way of working. But it just illustrates that to make a building like this, you really have to approach it from a completely different way of thinking.
With the steel megastructure in place, they turned their attention to the building's signature glass facade.
We wanted the glass volume to maximize views out, maximum light coming into the office environment. And what we looked at is to create a dynamic over the length of the facade, as if this building is in motion. And we did that by playing with faceted triangles that go from a flat facade on the south side to a completely faceted pineapple structure on the north side. So this transition makes that when you observe the building from distance, it seems to be in constant flux with light, with clouds, with sunlight playing on the triangles. It seems to be a kind of moving object over this static classical building.
The finished effect means the glass is constantly changing as you walk around it. There's something of the effect of the glittering sea or fishy scales.
The gigantic extension was secure, glistening above the old firehouse. But there was still no physical connection between the two structures. How do you connect two massive buildings with the least impact possible? They decided to use the firehouse's old dry tower.
You do an extension to a building. At one place or at one moment, the two parts have a place where they meet together. What we see is maybe the only physical touch between old and new is the dry tower. When we see the dry tower, we see a little bit of masonry above the roof. And then we see a start of a glazed elevator shaft. The elevator starts in the old dry tower, go to the glazed shaft, and then enter in the new building.
Although you enter the lifts at the bottom of the existing building in the tower, the lifts take you up to the new building and connect, but the structure of these lifts is hung independently from the steel structure of the new building. So it's not actually touching the brickwork of the existing tower. The existing brickwork tower acts as a sleeve in which the steel structure is hung independently from the brickwork, completely loose from each other.
The amazing thing is that both of these buildings are separate. Replace the bricks, and good as new. Of course, that would be a very expensive change of heart.
The radical new extension was in place, transforming the original fire station, seamlessly combining groundbreaking architecture with a sense of history to bring a forgotten firehouse into the 21st century.
I think actually that our project allowed this building to be reinstated as an important landmark within the Antwerp urban fabric. There might have been all kinds of other scenarios where this building would have been demolished and something new would have been built. And I think it was very important also for Zaha herself to keep this existing building, to stay with this and to have a separate layer coming over it, to layer the city instead of demolishing and rebuilding stuff.
We have a larger building with a bigger capacity, working 500 people in it now. And we have also a remarkable site now here, a site maybe forgotten in the past.
What we have here is a building that deeply respects the original and gives it space. Yet it also reacts against it with something so crazy and outlandish. The overall effect is that we have these two structures that exist together, but have their own identity.
Deep in the heart of New York's Manhattan Island, one of the most prestigious addresses in the city has a new resident. An 88-story skyscraper, one of the highest residential towers in the world, It's classed as a super tool.
There's only about 146 of them in the world.
It's really become a club that people are desperate to be a part of.
Not just tall in the extreme. At just 28 meters across, it's also very slim and vulnerable to the city's wild winds.
432 Park Avenue is 15 times higher than the width at its base.
To create luxury apartments with unspoiled views, the engineers had to do away with internal columns. The project would cost $1.25 billion and push skyscraper engineering to its limits. This gravity-defying wonder is 432 Park Avenue. So how did they build it? It's 2011, and on a small plot in Manhattan, an ambitious plan is being put into action. To build a 28-meter wide tower, 426 meters into the sky. Dimensions never seen before in skyscraper engineering. Engineer Hetzi Mena was tasked with figuring out how to build this developer's dream.
It's not a normal, typical building. It's very tall, small footprint, it's very slender. There's a lot of challenges. It's a tremendous effort put in for over 5 years from start to finish.
This super tall, super slim design was difficult enough to build as it was. But there was another curveball coming the engineers' way. With apartments needing to fetch $75 million plus, no one wanted internal columns getting in the way of luxury interiors. They told the engineers to get rid of them.
Taking away columns is all well and good, but unfortunately they're very important for holding up the structure. If you take them away, then you need an alternative way to carry those loads down to the ground.
Columns are what make a building stand up. You take away that structural support and...
With a building this tall, you need a way to hold up the weight of 88 floors. Normally, this is done with internal columns. Without them, they needed a way to support this super tall skyscraper.
So like a typical 20, 30-story building would have a central core, what we call the backbone of the building, and that will hold the wind and the earthquake, seismic, horizontal forces.
This is the backbone of the building. It's what gives buildings their strength.
For 432 Park Avenue, at 88 stories high, that wasn't enough. The engineers decided to make the building's outer shell super strong to reinforce the structure.
This building has a backbone, which is also the central core, but we also supplemented the exterior columns, so together they are providing the stability that the building needs.
They inserted supersized steel rebar into the concrete outer shell for added strength.
To make concrete stronger, you put steel reinforcement into it.
And in this case, it's a gigantic piece of steel.
Architects Chuck Knapp and Gloria Glass kept a section of this super thick rebar as a souvenir.
You can see the size and the diameter. These are major rebar.
And in general, they are this size, you know, right?
Right. And the deformations on the side of the bar are normally not this. This is screwed because they need to be able to screw these into couplers. So it's a different animal, but it's pretty big. And this thing is only about an inch and a half, and it's very, very heavy.
It wasn't enough, though, just to have a super strong facade.
It had to be tied to the core of the building, that area that houses the elevator shaft.
This supersized rebar made the outside of the skyscraper incredibly strong, but the engineers made it even stronger, connecting it with steel beams to the concrete elevator shaft, which acts like a spine running down the length of the building. The skyscraper's core and reinforced exterior gave it the strength to tower 426 meters in the air. But this height made it vulnerable to New York's infamous winds.
A skyscraper is a structure that people live in. You hang out there, you sleep there, and if the architects and engineers don't do anything about the wind, then you're really going to feel it, especially if the building's thin.
All structures that we build move, but in tall structures, they're particularly prone to being moved by the wind. And the thinner the structure, the more vulnerable they are.
The skyscraper was vulnerable to turbulence created by the wind. If the wind was strong enough, it could make the building shake, making it uninhabitable and even risking damage to the structure.
When you have a tall, thin structure like this, and when the wind strikes it, the wind then wants to pass around the building, creating turbulence on the backside. That turbulence creates vortices, swirls of wind which pass up the full height of the building. And the turbulence creates the swirls to first be on one side, and then the other, and then the other. This is called vortex shedding, and what it does is it starts to actually buffet the building sideways, even though you're blowing it straight on. Now, any building has a natural frequency. Think about pushing a child on a swing. If you push the child at the right frequency, the child will start to go higher. Same thing happens to a building. If these vortices start to form and push the building at the right or the wrong frequency, then the vibrations will start to get out of control.
The engineers started to take out windows, letting the wind rush through floors that contain the skyscraper's pumps and other utilities.
Well, we found that when you make these penetrations in the building at certain locations, it reduces the wind pressures by about 20 to 25%.
Every 12th floor is open to the air. That lets the wind blow through. Really clever, but it doesn't solve the problem completely.
To make sure the skyscraper could even survive New York's strongest winds, the engineers had another trick up their sleeves. The masterstroke, the brilliant engineering trick, is hidden away at the very top of the tower on the 84th floor. Two secret giant machines that directly counteract the wind.
The wind acting on the building wants to make it sway. To stop that happening, then they've used tuned mass dampers, which means a huge lump of concrete high up in the building. It's an active system, which means that when the building wants to sway in one direction, the hydraulic jacks will move that lump of concrete in the other direction, counteracting that force and hopefully keeping the building not moving too much.
This particular building, we have a damper, weighs about 1,300 tons, absorbing the energy of the wind that exerts on the building. So it has to be fast enough so the occupant that sits in the apartment doesn't feel the movement of the building.
Which is good news if you've paid over $75 million for one of the incredible apartments.
432 is without a doubt a feat of world-class engineering. It cost a staggering $1.25 billion to build, and by my estimation, it's about as beautiful as a skyscraper can get.
.432 Park Avenue towers above the competition, giving one of the most sought-after addresses in New York its best view as well, using clever engineering to take skyscrapers to their limits. On the rugged east coast of Scotland, a shipbuilding powerhouse had fallen quiet. But all of that was about to change thanks to one extraordinary structure. The brainchild of one of the world's most radical architects. The Victoria and Albert Museum in Dundee rises from the River Tay, forming a man-made cliff. This revolutionary design forced engineers to construct a huge dam in the middle of a raging river. Build a gravity-defying 8,000 square meter shell in one piece of concrete without a column in sight. And hang 3-ton slabs off impossible walls.
It looks like the forces of this building should just completely rip it apart.
So how did they build it? In Dundee, Scotland, the city's industrial heart needed a kickstart. The radical plan was to build Scotland's first design museum in the historic shipyards where Scott and Shackleton's legendary Antarctic ship had been built.
It's been very important in this project to have a remarkable building. This is a new design museum, so it seemed right to look for an ambitious design that would inspire people to come and see the building. A building by an architect who was so brilliant at responding to a particular place, about the relationship between the river and the city.
Visionary Japanese architect Kengo Kuma designed this brutalist masterpiece. He used Scotland's stunning landscape for inspiration.
The opening island, we found a beautiful cliff. Reminds me the spirit of Scotland, because it's very tough, and the nature is very tough, but still the cliff is fighting with the tough natures. It reminds me the history of Scotland and the culture of Scotland.
The plan? To lay the foundations in the middle of the Tay River, whilst battling the Scottish weather and protecting local wildlife. To cast a giant concrete shell that uses nothing but its own strangely shaped walls for support. And hang the signature cladding with pieces weighing up to 3 tons from the gravity-defying walls. Their first task was to lay the foundations, but this wasn't going to be easy. The design called for a huge portion of the building to stick out into the Tay.
There are serious issues with building in water.
Building in water is incredibly difficult. You've got to hold back an entire river while you're building.
How do you lay foundations in the middle of a river? Structural engineer Dan Clipsome had to tackle this monumental task.
Building in the water isn't fundamentally different from building on the ground. The foundations of the building still need to go down to bedrock. So whether it's in the river or on the land behind the river wall, we're still piling down 20 meters into the rock to get a good foundation for the building. Dundee is a very nice sunny city most of the time. It's also cold and wet in winter, like many places. So the weather plays quite a key part in construction. We're working by a tidal river, working in a climate that has extreme colds during the winter, and rain and wind. They all need to be considered during construction.
They had to lay the foundations on a seriously difficult site. To make it possible, they decided to build a dam out of 12,500 tons of stone and earth, called a coffer dam.
Coffer dam is an enclosure built within a body of water to allow the enclosed area to be pumped out.
That means that you can get on with your work in a nice, dry environment.
The coffer dam would let the engineers extend the existing dockside, pushing the site into the Tay. Building the dam was a race against time.
There are protected species in the river, particularly a species of seal, and so we had a very short time scale that would allow us to build our foundation out in the river. We went on site in March in 2015, and we had to make sure that all of that work that was done out in the river was done by the beginning of June, the beginning of the seal pupping season.
The local grey seal population lives close to the site. Their breeding season was just around the corner. And the second it started, all work in the river would have to stop. They'd have to work quickly. The construction team hammered massive steel slats into the riverbed, filling in the center with rubble to hold back the force of the Tay River.
What was done in this case was a temporary bit of land was created. So the contractor installed a piled wall out into the river and filled it in with ground to create a new bit of land that we could then build the building on. We were constructing the building on top of solid ground, even though it was above the river.
The engineers drilled down 20 meters, anchoring the building's foundations to the bedrock on concrete piles. At the same time, they had to make sure the corrosive salt of the Tay wouldn't eat away the foundations. They decided to use a concrete with a special formula, specifically designed to resist salt.
Salt and chlorides are the enemy of our structure. So they cause corrosion and damage to the building over time that we have to prevent. The concrete mixes we've used in this building had to be different. We had to change them from what we'd normally do in order to make them more resistant to the elements, to the salts, to all of the things that are trying to attack the building.
The foundations were secure, and a new piece of land had been built into the Tay River, ready for the next step of the build. The engineers now had to tackle the building's radical shape. They wanted the walls to support the entire structure, removing any interior columns from the gallery spaces. But the leaning and twisting design threatened to tear the museum apart.
Normally, you would never build walls that are sloping outwards, and that's because as well as the usual gravitational forces that are pushing down on the building, you're adding an extra layer of strain as the walls are being pulled apart.
The shape of this building is really incredible and something that you don't see in architecture very often for a reason, and that's because it just takes a lot of expertise, science and maths to achieve what they've achieved here.
To get the calculations right, they used the very latest 3D computer modeling and sculptural techniques.
This is a building that is a very modern design. We needed to use a lot of computational power to create the design of this building. We looked at the shape at the concept stage, and we could have put a frame in here and hung the facade off the outside of it. It could have been a traditional building. The problem with that is we'd fill the building with a lot of stuff. And this is a museum, this is an art space, this is a gallery, this is a place for people to come and enjoy that we didn't want to fill with bits of steel and concrete. Historically, we'd build buildings with the walls carrying the weight. Stone huts back in the Dark Ages. The walls carried the roof, and that was how you protected you from the wind and the rain. So we took the option of using the shell of the building as its structure, kind of going back to the old way of doing things, make the outside of the building hold the building up, and then you don't need to put anything inside. Because of the way the building is pulling on all the different bits of itself, the roof pulls on the walls pull on the roof, we had to design it as one big object.
To make the most of the exhibition spaces, the architect didn't want any interior columns. To achieve this, the shell of the building, the exterior walls, had to support the roof and themselves. No easy task given their extreme shapes. The solution was to design the shell to work as one piece, using its own weight and steel reinforcements to hold the building together. But there was a problem. The shell would only be structurally sound when the last piece was in place. Until then, the whole building was unstable.
So the leaning walls and the whole building is really held together by these tension forces, pulling everything back towards that central core.
The skin of the building itself is doing all the work. It's carrying the weight of the building, it's pushing and pulling with different forces, it's resisting the wind and the rain, it's keeping the building watertight, holding the facade up and the cladding on the outside, but it's primarily supporting the building.
They used their advanced computer model to make the walls super efficient, making them as thin as possible and, more importantly, light.
That resulted in some of the walls being half as thick. They went from 600 millimeters down to 300 millimeters, which is a significant saving in materials and reduces the weight of the building, the size of the foundations. You know, there's a lot of positive outcomes from that.
Now they faced the challenge of building the 2,300 cubic meter shell. This would only be stable when the last pour of concrete had hardened. It wouldn't be able to support its own weight until the very end.
Because of the shell we had to make, it was like casting a giant mold. We had to finish the casting before we could take the mold away, because in a partially completed state, the building isn't stable.
As the shell started to go up, the builders had to add more and more formwork, the molds that hold the concrete, to support the precarious structure. If they removed a piece too early, the whole structure would collapse. After a year and a half of constant work, the last concrete pour was completed. It was time to take off the formwork and see if all the calculations were correct, and this one-of-a-kind design would support itself.
Finally, after nearly 2 years of it coming into place, it came down. And it was a very, very exciting moment to see that formwork removed and the shell of V&A Dundee finally born, finally revealed.
When the molds were removed, the black concrete underneath was revealed, colorized with PFA paint or pulverized fuel ash made from the waste of coal-fired power stations. At last, the V&A's groundbreaking shell was complete. But architect Kengo Kuma wasn't going to leave it there. He had big plans for the finish.
Instead of vertical wall, we tried to bring that kind of pure natural formation to the building.
He wanted to use giant concrete blocks to mimic the craggy appearance of Scottish coastal cliffs. But it turns out creating a random natural pattern is harder than you think.
If you look at the facade of the building, at the external panels from outside, you'll see that they all look slightly different. There's a random pattern to them. They step in and out, they step up and down, they kind of weave around and create this sort of vision of this cliff face, of this random assortment. In reality, they're not that random. If we did an entirely random pattern for the facade, if every plank was just generated by some mathematical formula, the risk is that 2 or 3 planks next to each other would look similar enough that your brain would see them as the same. So we had to create this algorithm that allowed us to fine-tune things to make sure the architects could look at the building from every angle, and they could tweak and adjust until it looked just so.
With the shell working as one piece, it was ready to take the massive weight of all the cladding. All in all, there are 2,500 pre-cast rough stone panels, weighing up to 3,000 kilograms each and spanning up to 4 meters. Hanging them was going to be a challenge.
The facade panels are made from a concrete and reconstituted stone material. They weigh an awful lot. The facade, the panels, weigh about the same as the wall that's holding them up. Panels on a more vertical wall are smaller, panels on a more sloping wall are bigger. That presents another challenge because the walls that are sloping and twisting are working harder and the cladding hung off them is heavier. So it's a sort of double whammy of challenge that we had to overcome in the design.
The anchoring points of the giant stone cladding had to be seriously heavy duty. The engineers decided to set them in the shell when it was first being poured, letting the outer shell harden around them. This, though, left no room for error. Get it wrong, and the cladding wouldn't fit on the shell. In the end, every anchor, bar 3, was in the perfect position. The exterior of the building was complete, a testament to the Scottish landscape. The V&A Dundee is proof that radical engineering can breathe new life into a long-neglected area, using the natural environment to redefine the urban landscape.
The end result is a beautiful building that is truly built to last, as tough and rugged and as beautiful as the Scottish landscape that inspired it.
Dundee is falling in love with its waterfront again, and people that come to experience V&A Dundee now have a new relationship with the river, which has been such an important part of this city.
Extraordinary engineering challenges have been overcome to create the designer's vision.
I would consider this to be a landmark project. I find it fascinating that people look at it as a piece of engineering as well as a piece of art and architecture. It's a visible piece of structural engineering.